What if a plant could tell your robot exactly when it needs water? In this project, you'll use an ESP32 to read soil moisture, make smart care decisions, and share plant status both locally and through an IoT dashboard. You've already built the core pieces: sensing with inputs, acting with outputs, moving with motors, and connecting over Wi-Fi. Now we'll combine those skills in a smart farming project where an ESP32 monitors a plant and sends useful data to an IoT dashboard. Here's the mission. Build a robot that notices when a plant is thirsty and responds intelligently. The ESP32 acts as the brain. It reads soil moisture, decides whether the soil is wet, okay, or dry, then triggers watering, alerts, or dashboard updates, just like systems used in smart agriculture. The plant care system works as a chain of jobs. The soil moisture sensor is the input. It turns soil wetness into a signal the electronics can read. The ESP32 is the decision maker. It reads that signal, compares it to a threshold, and can send data over Wi-Fi. If the soil is too dry, an output device does something useful, like switching a relay, driving a pump, or lighting an indicator. Finally, a dashboard or display translates the system's state into information a person can understand. A soil moisture sensor is like a water thermometer for the plant. It does not know dry or wet by itself. Instead, it produces an analog voltage that changes with moisture, and the ESP32 reads that voltage through an ADC pin as a number. In one setup, dry soil might read around 250, while wet soil might read around 780. Those numbers are examples, not universal rules. Soil type, probe depth, and electrical noise can all shift the reading, so sensor values need to be tested and interpreted with thresholds. Calibration gives the ESP32 a personal scale for one sensor and one growing setup. First, take a reading when the probe is in dry soil, or even air, and save that as the dry reference. Next, take a reading in fully wet soil and save that as the wet reference. Then choose thresholds between those two numbers, so the program can label readings as dry, okay, or wet. Always test the result in real plant soil. If you change the probe, soil mix, or pot, calibrate again, because the numbers can shift. Before wiring, start with power disconnected. Connect the sensor VCC to the voltage your module requires. For ESP32 projects, prefer 3.3 volts unless the datasheet says otherwise. Connect sensor ground to any ESP32 GND pin, so both devices share the same electrical reference. Then connect AO or analog out to an ADC-capable ESP32 pin, such as GPIO34. The key safety rule is simple. ESP32 inputs are 3.3 volt logic. Do not feed an unknown 5 volt sensor output into an ESP32 pin. Once the ESP32 has a moisture number, the program has to compare it with something. In code, you define thresholds that separate dry, acceptable, and wet soil. If the reading falls below the dry threshold, the plant needs water, so the program might turn on a pump, light a red LED, or send an alert. If the reading is in the OK range, nothing changes. If the soil is too wet, watering stays off. Because readings can jump, add a short delay or average several samples before acting. A pump is a bigger load than an ESP32 pin is designed to handle. The GPIO should send only a control signal, not power the pump directly. Use a relay module, transistor, MOSFET, or motor driver to switch the pump's separate power supply. If you use a transistor or MOSFET, the ESP32 ground and pump supply ground usually need to be connected together. For classroom work, keep the pump low voltage DC, keep water away from all electronics, and always check wiring before turning power on. When the ESP32 decides the soil is dry, the robot should water in a controlled burst, not continuously. It switches the pump on for a short window, usually 2 to 5 seconds, then turns it off. The tubing should guide water directly into the pot, away from the electronics. After watering, the system waits a little, because moisture takes time to spread through soil. Then it reads the sensor again. For safe testing, replace the pump with an LED first. The same logic still applies. Before connecting to an IoT dashboard, give the system a local voice. A green LED can signal healthy soil, while a red LED or buzzer warns that water is needed. The serial monitor shows raw readings, which makes testing and debugging possible even without Wi-Fi. IoT monitoring turns the watering project into something you can check from another room. The soil sensor sends readings to the ESP32, and the ESP32 either connects to Wi-Fi or creates its own small web server. A phone, tablet, or laptop opens that page and displays the important values: moisture level, plant condition, and whether the pump is on or off. The page can be refreshed manually or updated automatically for near real-time feedback. This makes the system more practical because students can monitor the plant without standing beside it. In code, the plant monitor becomes a simple loop: read, decide, act, report. First, analog read gets a raw moisture value from the sensor. Then if, and else logic compares that value with the thresholds chosen during calibration. If the soil is dry, the program can turn on a pump, LED, buzzer, or relay. If it is wet enough, it turns them off. Finally, the same status can be printed to a screen, serial monitor, or online dashboard, so the system is easy to check. When the robot does not behave as expected, debug it like a scientist. Change one thing at a time, then test again. Start with the sensor. Confirm power, wiring, placement, and calibration, and watch the serial monitor for real values. Next, isolate the pump circuit. Before connecting the pump, test the relay or driver with an LED. For dashboard problems, verify the Wi-Fi name, password, IP address, and error messages. Once the system works reliably, you can improve it with logging, water level sensing, battery power, or support for multiple plants. Project 9 connected the full pattern: sense soil moisture, decide when watering is needed, act through a relay and pump, and monitor results online. The big lessons are calibration, safe power control, and making data visible. Next, you'll reuse those same ideas for security: detecting motion, triggering alerts, and building a smarter ESP32 monitoring system.